Right. Oops. Okay, we don't have a way to get notes up to the screen. Can you do it? Thanks, Troy. Here, I'll move this. Where's the RGA? Okay. So before we start, was there any follow-up that we still need to talk about from the last session? Are we all good there? Okay, let's run out of time. All right. So this session we renamed after taking a look at what we've been talking about with Opt and realized that we don't have. We've been talking over the last year in kind of hand-wavy terms about, well, we have UEFI, and we've got secure boot, and we've got ARM-trusted firmware, and all these things are going to kind of work together, and we'll have key storage, and we'll have all the bits and pieces that we need. But we don't have a design on how these things are actually going to work. So this session, this is an impromptu session. I don't have a whole lot of slides. I don't have a lot of detail on exactly what we're going to talk about, and I'm not going to present. What I want to do is I want to talk about some of the topics, and it's an open round table for us to hash out these ideas, figure out what we need to talk about, to then go away and start putting together a design of what a reference implementation would look like. I mean, my goal is that between now and the next Connect, we can start working on what are the pieces we need, how do they work together, and actually put that stuff in place so that we can have, one of the things I'm concerned about is secure boot. What are the other security and firmware issues or problems that we need to solve? So here's some of the topics that have come up recently. UEFI secure boot we've been doing UEFI specifically for leg over the last year. And secure boot is the topic that always comes up. But it's, we got to get it working first before we even talk about turning on the secure boot features. At the same time, most of the segment groups are saying, we know, sure, UEFI for enterprise, but we're all committed to U-boot. We use it on all our products. We want to continue to use U-boot, but we need to have we need to have verified boot. We need to have signed images. We need to have a method for doing trusted updates to the firmware. If we're doing secure boot, how do we handle the keys? How do we handle making sure that those key databases meet the requirements of secure boot? Are they tamper resistant? Do we have secure updates to them? ASLR, KSLR, what are the implications for firmware? Are there any other services that we want to be providing to Linux that we can do in a reference implementation of, so Linaro does a release, and this is an example of how to do DRM with the secure world in a way that is both, was technically sound, is open, all open source, so that someone who has their hardware and has control of their hardware can use it for their own purposes, and is also useful for our members to be building products. And then we have some issues around kexec and secure boot, where what do we need to do if we're kexecing from one kernel to the next? Well, now we've got some requirements on the kernel to not go and boot a kexec another kernel that's insecure, and what are the bits and pieces that we need to do that? So I think I'd like to start off with secure boot. So I had a conversation. Where's Art? Sorry, there's Art. Art and I and Olivier had a long conversation yesterday trying to hash things out. What we have right now is we have ARM-trusted firmware, which defines the different stages of the bootloader. So I'm speaking specifically of AR64 here. or sorry, ARMv8. Is that the right way to talk about it? So specifically talking about ARMv8 here. What's that? ARMv8A. We're specifically talking about ARMv8A, where we have BL1, BL2, BL3, and then BL3 has the three parts, one that runs in EL3, one that runs in secure EL1, and then the one that runs in normal world EL2. We have defined very well of what those stages are, which is like, great, we know how U-boot gets onto the system, or you know how UEFI gets on there. What we don't have is once we get to UEFI, what has to happen so that UEFI is able to provide secure key storage? When we're talking about it, realize, we don't want to have any, part of the design of UEFI is we don't have to have any keys on the device. Or we don't have to have any private keys on the device. It's all the public keys because we can verify signatures and only operate if we verify a signature. However, we don't have if we're only operating within UEFI proper, we don't have any technical mechanism of having tamper-proof key storage. If we've got flash, well, what's to prevent the kernel or some malicious application to come in and go and overwrite that flash, or even if U-boot verifies that the flash updates are correct, it still can be tampered with by the kernel erasing a sector. And the only way to protect against that is to have some kind of secret in the device. But if the secret's in the device and it's in normal world, the malicious application can find it.
At the same time, you want to make it really easy for authorized users to override and want to make it impossible for unauthorized users to override.
Yes. Yeah. So I think we've come to the point where we know we need to have stuff in secure world. Some of the engineering constraints around this is, well, how do we actually implement that key storage? Some of the things that have been floating around is, on some devices we're going to have flash, NOR flash. On enterprise, like on servers, it's actually pretty easy because all the flash on the system, we can just say firmware owns that. And we don't have to worry about how it's going to interact with the kernel wanting to access that same storage device.
Is that true? We can also have the UEFI non-scheme. The kernel used to set root options with a single flash device. You can't just say this flash device is owned by firmware and secure updates, because you need to set the root device and next boot and all kinds of UEFI variables.
That's the work of real-time services, so it's still delegating the modification of the flash to UEFI.
Okay.
So the kernel asks UEFI to do it. So we're just talking here about some privilege separation between what's happening.
But you still need events. You can't. It still requires some secure world stuff to make some of this stuff really secure.
Do we get the notes up on the screen?
Yeah, it doesn't work. I can't get it.
It's not, okay.
I can't.
Okay.
It also depends on what comes between UEFI and the kernel. And on x86, you may have two other things running in between. There's one wrapper, and then there's grub. If we have
Right.
the same thing.
Right.
These
Well,
can have key storage elsewhere.
So I think we figured out that we weren't able to figure out any way to do what we need to do without the secure world being involved. So the first question that I've got for discussion is, do we do key storage in OPT, or do we try to do it in ARM-trusted firmware?
Why do you even want to give access to U-boot to the key store? Even current implementation of a verified U-boot relies on the establishment of root of trust when you load your U-boot, and you include the keys within U-boot as well, right? And then you can keep those in memory, or if you want to, you can put them in secure memory. So that way, you're just building up on the root of trust from the component that loaded you into memory. And once you're in memory, then you can use whatever you carry with you.
Okay, so, but how do you support then updating those keys? That's where things get, if everything is static, If each component never gets changed or is only updated with a newer version, that's okay. But if you have to have a key database and you have to do revocation or add keys into the database, how do you know that those updates are actually valid?
So, you have a key delegation structure where you have different keys for different things, right? And for example, for U-boot, you could add a simple key that would allow you to authenticate your database of keys. They don't have to be secret or anything, they're public keys, but as long as they're assigned with the correct key somewhere else, you can authenticate it with the key that you are carrying with you. So if you have to do key revocation or updation of your keys, you only have to update your database. Now, if you have to revoke the key that is in your U-boot, then that's a different story, because mainly either your U-boot or that key was compromised, so anyways you have to revoke that U-boot, so you just reflash that one. And then about revocation about that one, it's a different topic, right? But at least revocation of the existing key store that you're using for authenticating further components after your bootloader could be easily achieved with, I believe, could be easily achieved with what it's already available.
Okay, so the question, or what has to be answered there is, do we care about preventing rollback? Because if you've got signed key updates and you just store those into Flash, it's like, great, we can verify that those are correct. What that doesn't protect against is another application coming around and just erasing them and putting the old ones back. So it's the rollback attack. And two questions. One is on U-boot, or sorry, on UEFI, we have to care about this because on UEFI is part of the spec, and it's part of how all of our secure boot works. For the U-boot platforms, and this is where I want some feedback. Do we care? I think we do. And if we do, how do we implement it? How do we ensure that? And I think that the key storage is, I think it's the same problem whether we're talking about U-boot or UEFI. And I think we can use the same infrastructure. How do we do it?
But you would need secure role defraction for that. And but we're not accessing the secure storage from the LTE. That's my main point. It doesn't mean that we do not need secure role to enforce the anti-rollback. But at least we don't need the secure role to access the real storage that LTE would have. And that way you're not compromising earlier or on your
Okay, so with the key storage, what we talked about yesterday is if firmware, when firmware is coming up, when it's just firmware, doesn't matter because firmware's in control of talking to the storage. When we've got UEFI, we have the problem of we've still got runtime services where all of these updates happen. That runtime services can do an operation that's going to cause a write to the key database, and so the secure world may ask for a write to RPMB. Is that right? Rollback Protect Memory Block. It'll ask for a write to it, but the kernel may decide to ignore part of those requests or not do all of them. And I don't know what the protection on the eMMC controllers is to make sure that that attack is protected against.
Well, that's where security comes in. If you don't get service, then you just don't proceed. Or you have your secure implementation of your eMMC driver insecure. A little piece of it that is the one that allows you to do the update on your RPMB. You don't need the entire driver there because you're not concerned about that. You only need that kind of like a counter or increment functionality available.
Okay, so that's what we need to. So that's one of the design constraints that we need to figure out is how can we, if we use RPMB, how do we actually expose that to the kernel? Because it's complete with UEFI completely breaks the runtime services model, and that's a big problem. It may be that we just decide that we don't care about it.
Right now, you're assuming that you have RPMB as well. So it would depend on which architecture or which implementation you're designing it for. But as long as you have a mechanism to enforce or prevent rollback, then whichever actual implementation you use is your choice, basically.
Right. So what I want to add, one thing that I'd like to know is what I think that for Linaro, what we should be doing is again a reference implementation. I want to have a full multiple pieces, have secure boot enabled for U-boot and for UEFI, doing that key storage. What is the hardware that we actually care about to do that on? I think we need to have it running on Juno. I think we need to have it running on FTP. I think we need to have it running on QEMU. But those are not real hardware platforms. How do we? What are the platforms that we should be targeting, or what are the use cases that are most important to, you know, what do we think is the most important as engineers, and of course also for our members, what are our members asking for?
If it's just a reference platform, if it's a reference code, then it doesn't matter if it's not really secure storage. You just want to have something on your reference platform that is as close as possible to being in the right place, but your reference code is then going to need to be ported and certified on a real platform.
Is it sufficient if we do that for that we can actually have some confidence that we're doing the right things if we're only doing our private platforms?
You're never going to implement a reference code that's going to match various SoC manufacturers' implementation of the secure key storage. I mean, it's done in different ways, and I mean, it's supposed to be kind of hidden and different and value add. So there's no point trying to replicate that. You just want to create the mechanism for getting it down into the secure world and then leave them to implement the actual firmware that goes and reads the key securely.
It's probably possible to define a porting layer for that, and that will be instantiated on each particular hardware platform.
That's not interesting, right? I mean, that's not the interesting, right? Really, the driver that writes to this specific secure memory or this specific secure memory device is about as interesting as, you know, a flash writing driver for anything. That's the interesting is what's the interface to getting to the point where something calls that thing that does it. And a reference design, even if it's, you know, even if no one's going to take that code and use it, having a reference platform where you can actually see each layer in the software stack is useful for people to see how to implement it. Even though you just throw the bottom one or two layers away and then write your own platform.
And primarily, which layers goes into which product, but I think that's the key question.
So, I'd like to hear opinions on how we should actually do this. So, what layers? Where do we need to put guys? Where are the layers? What layers need to be involved?
Well, it's quite obvious that not only the key store itself should be insecurable, but everything that reasons about the validity of the updates and authentication of what gets passed into the certifiable protocol all needs to reside in the secure world to have a meaningful, to allow a meaningful implementation.
I think that's right eventually. I'm just wondering whether there's a short-term step, if you don't mind, that updating the key database is linked to updating the firmware. You have to have a new U-boot or UEFI if you want to update your key, then you can just lock it in within the normal world firmware itself and rely on the facilities within the trusted board boot, as we call it, in on-trusted firmware, which has a firmware update mechanism and anti-rollback facility, and then you can worry about those secure storage bits a little bit later.
Yeah, I think we have to tackle the secure storage pretty quick. No, we can turn the feature on in UEFI for secure storage, but it won't actually be secure until we have that interface into the secure world. And until we have that, we're not spec compliant with UEFI secure boot. Except what you're going to say. Okay, so you were just saying, we need an end-to-end project. We define an API, put the key storage bits into opt and a runtime services driver that uses that, and also a U-boot port to make use of that.
So you guys have access to you have access to a secure timestamp?
I don't think so on the reference platforms. What are the requirements on the hardware?
Well, you have to do, it's more of a comparison thing, actually. Also, it actually doesn't require that you have a timestamp unless you're going to create new certificates yourself. As long as you're just comparing them, you just have to make sure that one's greater than the other. So it shouldn't be a big thing.
So, from reading what I can read on this spec, or from what I've read, it seems like trying to create signatures on the device itself is really...
It's an alternate. It's not a spec requirement.
Okay.
This way. Back a bit to what portion is doing the verification of the certificates, which ARD seems to believe needs to live in a secure world. What happens on x86 at the moment with respect to secure boot and SMM, I guess, or where does that live?
Okay, there's different implementations. So let me give you the typical EDK2 sort of tianocore.org story. Yeah, you're going to switch in. You're going to switch into SMM, verify the certificate in SMM, and then after that's complete, you'll write to it. Most x86 hardware gates the access to the flash part after a certain part of the boot, so that you can only access it from within SMM. You can only perform write cycles from within SMM. So therefore, once you're there, you've got access to the same NOR flash that you're booting out of. We validate the certificates in SMM today. That's fairly typical. And there are some implementations we use a coprocessor instead, like you would think of it like an SCP ARM, an ARM 9th core or something like that. You have an extra core that all it does is handles the secure storage, and secure storage is actually managed by that coprocessor. Those are the cases for some x86 derivatives which have limited SMM capabilities.
So how do I update the primary key, like the root of trust on that? If my attack scenario is not I'm protecting against someone maliciously overwriting my firmware, but I'm protecting against someone already shipping me firmware that has been hacked and I want to build myself.
So typically you can revoke, the user can go into the user interface in most PCs and simply turn secure boot off, and at that point you can update anything.
Yes, but then I want to have secure boot turned on again.
And then you turn it on.
And
By enrolling the PK turns on secure boot.
Okay. There's the two keys. There's the PK.
Yeah.
There's the
K. There's a KK, which is a list. Yeah.
And then there's 3 databases.
Yeah. Dong's probably better. Dong's here, so he's probably better at handling this. Dong's over there. But, no, so basically, usually the user physical presence is a requirement that from the UEFI that says you should be able, with physical presence, be able to turn this off. That's very typical implementation requirement. If you want to do flash update of other things, that's usually done through a different mechanism for overriding all of flash. I want to refresh my entire image. I would say UEFI doesn't specify how to do that, but could use capsule update, which is a different API that you're not even talking about yet. So for firmware update. Secure capsule.
If we're going to do that, we probably still need to go into the secure world.
Yes. In the ARM, you
send that whole capsule to the secure world, get the signature verified there, and then the secure world decides what.
That's right. So in the x86, there's usually a split between the part which actually does the authentication and the part which does the device, the actual flash write, and that's usually the architectural division in terms of where do I put my, this part is board or SoC specific, and this part up here is the kind of common code which manages authenticating things, allocating the buffer, managing the buffer, that sort of thing. So.
Okay, so we're going to put it in opt and define an API and everything good. Any other comments on this before we go on?
Okay, I came in late, but I wanted to know if it was discussed about KExec repo.
So what do we do about the set variable at runtime? So in this case, we don't support it. Or...
Oh, that's a good question. Okay, so one of the things we talked about yesterday was we can check the signature on, like we can have UEFI check that grub is signed or that the kernel is signed. We can check if the initRD is signed. We could even check if the DTB is signed if we wanted to. We don't do anything right now with the kernel command line. And with the kernel command line, we can end up doing all kinds of interesting things. And I think this is a problem that spans, it's not just ARM, it would affect x86 as well. What do we do? What are valid things to, what are the rules for kernel command line? Should we be able to set a kernel command line at all when secure boot is on, or how do we make sure that the command line is valid? That goes for U-boot as well.
From U-boot perspective, or at least on Android mode, it depends on how you say that you're constructing your command line, right? It could be part of your route disk, or it could be something that you're passing as a primary. So I guess it would be information dependent.
Yeah.
Whichever way you're thinking, if it's in the round disk, as long as you authenticate the round disk and the kernel image, you should be fine. And if you're taking it from your U-boot environment variables, then you should authenticate your environment variable partition.
Well, that depends on who's setting those variables in there. If the variables can only be set through the U-boot user interface, then that's fine, because you're running a trusted environment. There's no way for something running under a kernel to update that, as long as those variables are in secure storage at least, which they probably are not at this time.
Yeah, so the fundamental issue there, of course, is that the command line needs to be set by an installer. So it's by definition something that happens on the device itself, and it's not something that comes down from whoever owns the private key that you're trusting.
So is this, are we going to just have a private key in the installer to be able to make a change, then sign that boot variable or that configuration file?
Well, you can't have a private key in the installer. If you have a private key anywhere, it's going to be in a secure root.
Yeah.
So, thing is, so if you're going to ask the secure world to kind of sign off on your new command line, how is secure world going to authenticate you as a client transmitting that request?
Yes.
So
what does x86 is anything done for this in x86 right now, or is it not addressed? Don, do you have any?
I'm sorry, I didn't follow the question.
What is done? How is the kernel command line authenticated or checked before booting when secure boot is on? Does any of that happen? Or does UEFI just hand off to grub and then say, grub, it's your problem?
Yeah, well, the secure boot itself, the scope is stopping at the line when the UEFI hands off to the shim, right? And then the shim gets the grub and so on. So the policy of how Linux is actually handling the the verification is kind of beyond what UEFI is defining. But I think on the x86 side, they have extended what's called a MOK, right? So they have the ability to extend the database for the keys. So the Linux side can use extra keys to authenticate what goes on afterwards.
I think we need to. I don't think we can really solve this one here. I think we need to. I need to go and talk to Matthew, Garrett, and James Bottomley and get more information about.
Right.
That.
Yeah. Those people are the key architect for that.
Because the other thing you have is that depending on how you're booting, you have multiple ways in which the kernel command line can be set. If you use grub, you have a grub config file.
And if you have U-boot, you don't have grub normally. So
Yeah.
if you only have as long as you have U-boot, you can only set it in U-boot or override it from U-boot, but it will be a combination of the DT and.
If you have grub under U-boot,
Huh?
if you have grub under U-boot, you have the same problem.
Does anyone do that?
It exists.
It works.
Not for 64-bit, but
Okay. Okay.
No, I don't think many people use it. It was get our feet wet, get things working. But it makes so much more sense in UE5. I think we can probably move. I think we've talked this one to death. I think the next one that would be good to talk about is what we need to do in KExec scenarios with secure boot. So, Jeff, you're most familiar. You want to talk about KExec as well? So,
yeah, I'm just wondering, will we be able to support KExec reboot to a secure space?
okay, so we talked about this. Art and I and Olivier spent a bit of time talking about this yesterday as well. First, kind of what we thought needs to happen is we need to verify the signature on the kernel, and we probably need to do that. We could do it with the keys that the kernel has itself, but if we care about the revocation lists that UEFI has, we might want to validate that signature with the UEFI key databases.
Are those available in the first stage kernel? So a little bit of background.
A little bit of background. So traditionally what happened was the user space prepared the image, but there's been, since I think the last RC or whatever, there's a new syscall there that allows you to load the images loaded. The entire image is loaded. There's loaded and prepared in the kernel. So in that case, with that syscall, you can do some kind of verification of the image, I guess.
Yeah. So I think what we figured out we need to do is, if we're using device tree, the device tree has to be prepared all within the kernel, because we can't provide it for user space. We don't have the same level of trust for user space. The kernel can be signed, the initRD can be signed, and then we've got the same problem with kernel command line that we need to figure out.
So you would only allow passing an unmodified device tree to the next stage kernel. In that case.
Well, it would still need to be modified if we were like changing the kernel command lines.
Right, but all the device descriptions. Because one of the traditional use cases for doing this is that you load a kernel that can deal with whatever boot interface you have, and has a preliminary device tree that describes the devices more or less, and then you have a user space tool that puts in the correct device tree that describes all of the hardware, and then you do a KExec with the right kernel and the right device tree. You would be able to do that.
Is that a big use case for using UEFI? Because that's a use case for using that first stage levels as boot.
Could be if people screw up UEFI and it only comes up with ACPI or broken device tree and you can't change it.
With regards to a broken device tree, if you have a first stage loader like Grub, you should be able to load that into a configuration table, I believe, at runtime.
Yeah.
So at that point, that's not so big a concern. At which point, I don't think it's necessary that that first stage kernel needs to touch that DT at all.
I don't know how this is done on the enterprise architectures. Like both 390 and PowerPC are now using kboot for booting, and I would expect that they have secure boot by now, but I'm not sure about that.
I believe it was changed. The DT handling was completely within the kernel. I think there was some work done.
Okay. Yes. So 390 doesn't use DT, of course.
Yeah.
PowerPC does.
Yeah. anything else? Oh,
So, well, regarding the check against the revocation list in UEFI, I had a look at shim source code this morning, and actually shim only authenticates against its own built-in certificates and the MOK store, basically. So even shim doesn't go back to UEFI itself.
Right.
To look at DB or DBX.
That's probably all we should worry about to start with. Let's get that working first before we try to do anything more exotic.
Well, yeah, so the problem with shim is that it's not something that it does install a protocol that grub can use, but once you're booted, you can't go into the shim anymore.
Right.
So for KExec, that wouldn't be accessible. So you really can only authenticate against what's already available in kernel.
Right. So we'd either have to extract all of the key store and cache it, which...
Well, you could potentially do that before calling execute
we
services.
could do that in the stub.
Load the
if
keys.
we really cared about it, we could do it in the stub and then just hold all those keys in memory. So there's a way we could do it. We're rapidly approaching the end of our session. This secure boot is the one I most want to talk about. Is there anything else regarding the way that firmware interact, or the different components interact, that people would like to talk about that Linaro should be working on between now and the next Connect?
Well, I have a question, which is whether Linaro intends also to integrate all the way down to the IAM architecture, the integrity measurement architecture for Linux. Does it all plug? Does it plug in well into that?
Joakim? I haven't talked about it at all. Yeah, I don't think we've looked at it yet. And we're still looking at this level of stuff. And I don't know enough about it to answer intelligently. Maybe we should talk afterwards. Who was first? Here, Mark.
With regard to the way bits of firmware work, we were on about U-boot, secure boot. If we're doing that, is there any plan to do any ARM-trusted firmware plus U-boot work? And is that going to be upstreamed?
Absolutely, if I have anything to say about it. I think what I want to see is I want to see two reference platforms. I want to see a full stack of ARM-trusted firmware, Opt, and UEFI, and then exactly the same thing with U-boot. Because I don't want to muck around with a whole bunch of different options of ways that we could support things. We have a T, we have a solution in ARM-trusted firmware. I think it's really important to have those upstream, like that, and board support for all the platforms we support in the upstream projects. And that may be a little bit difficult with ARM-trusted firmware or Opt. I'm not sure how the project. I'd really like to get platform support mainlined, as long as the upstream is supporting that. Cool.
Just a question. Are we able to link Opt into U-boot license-wise?
It would be the other way around, where U-boot would be a payload.
Okay, I thought of the case where
It doesn't have to be linked.
Okay.
It doesn't have to be linked. They're separate binaries.
Right.
But
then
there's a packaging question. Actually, there would be no problem license-wise putting them all into the same package, as long as the vendor is okay with shipping GPLs binary.
That was the case I was wondering about anyway.
It's all BSD license. This is all code that we can work on. We can have a full open source stack, and what I really like about it is we can get it into the hands of any developer.
Yes.
And it's like you've already got QEMU, off you go. Or we can get you a license for FBP, off you go. You can spend some money and get a Juno, off you go.
Yeah.
There's three platforms right there. And the plan is for, like what we're talking about with the Linaro community boards, is to see if we can get a fully open, secure world, so that we can do development for these things on those platforms as well.
So I was more wondering about the case where we have an SoC that can do secure world, but doesn't normally, so this, the U-boot comes up in secure mode, and then you can start off Opt on the side, and then...
Yeah. Well, okay, so here's a question to throw out there. I've talked a whole bunch about ARCH64A, or sorry, ARMv8A. Do we need to be doing this for RMB7 as well.
That was my question. The home group's going to want verified G-root.
So we need to do it for RMB7, period. Okay, RMB7, that answers my question.
This is just for consideration after secure boot. Have you guys considered about doing some runtime checks or runtime integrity checks of software or firmware that has been loaded or authenticated? For example, if you spend a lot of time in U-boot, maybe you're not going into boot the kernel, but you're doing something in U-boot, flashing or something. Some kind of integrity check so that you prevent yourself of getting clobbered by some malicious use of.
We've not talked about that at all, so we should talk more on what that would look like. So, I'm not even sure how to scope out that work.
Yeah, I'm not sure which company you're from, but we in Armstrong, we've spoken to some people who have expressed interest in that, and we would see that as something sitting as a special service within the trusted firmware space, on our V8A at least. But we haven't really thought about it a great deal because we don't really understand that technology either too much. But
okay, I'm going to wrap up right here. So if you have any further questions, just come and talk to me. Thank you very much. This has been very helpful. I hope it gives a bit of an idea on where we're going or what we wanted to do. So.
It's LMG, not RMB7, not LMG.
Yeah. Okay, we'll fix that. All right, great. Thank you very much, everyone.